Hello friends, I welcome you in lecture number 6 on higher order partial differential equations. In previous lecture we have discussed about the solution of homogeneous linear differential equation with constant coefficients, which we write in the symbolic form f d dash z equal to 0, and we have discussed the case that this function of d and d dash is non-homogeneous. We have discussed that what is the form of general solution if this operator of d and d dash is non-homogeneous, and if we are able to write it as a product of linear factors. And this is the summary of lecture 5, that if our function f d d dash is non-homogeneous function, and if we are able to write f d d dash as a product of linear factors of the form bd minus a d dash minus c, then we say that f d d dash is reducible, and the part of general solution corresponding to the linear factor bd minus a d dash minus c is given by this formula e raised to c by b times x and arbitrary function of by plus ax if b is non-zero, that is if coefficient of capital D is non-zero. Now if b equal to 0, then this quantity is undefined because here b is in the division. So in that case, if this coefficient of d dash is non-zero, then this will be the formula for the general solution corresponding to this factor e raised to minus c divided by a times y, arbitrary function of by plus ax. We have also discussed that if we have this type of non-repeated factor a d dash plus c, then this is going to be the part of general solution corresponding to this a d dash plus c. So in this lecture we are going to discuss some problems in which we will have this type of situation, that our function f d d dash is non-homogeneous, but we are able to write it as a product of linear factors, that is function f d d dash is reducible. I have taken several examples to explain this concept. First example, solve the partial differential equation d square minus d dash square plus d minus d dash times z equal to 0. This question was asked in GTU summer 2020 exam. Here we can observe that function f d d dash is non-homogeneous. We can see that degree of this term is 2 and degree of this term is 1. So degree of each term is not same, therefore this function is non-homogeneous. But we can write it as a product of linear factors. We can write d square minus d dash square as product of d minus d dash times d plus d dash, and this we write here in the bracket. And we can see that again we can take this bracket common, d minus d dash. Here we are left with d plus d dash and here with 1. That is f d d dash is reducible. We are able to write f d d dash as a product of these two linear factors d minus d dash and d plus d dash plus 1. Now as we have discussed that if we have linear factor in this form bd minus a d dash minus c, then the part of general solution corresponding to this linear factor is e to the power c by b times x, arbitrary function of by plus ax. So we will compare these two factors d minus d dash with this standard form, and we will write down the general solution in this form. Corresponding to d minus d dash, first we write for d minus d dash. For that we compare d minus d dash with bd minus a d dash minus c. That is, we have to see what is coefficient of d here. It is 1, that means b equal to 1. And if we compare this minus d dash with minus a d dash, then we find that a is 1 and there is no constant term here, that is c equal to 0. And what is our formula corresponding to this type of factor? E raised to cx by b, arbitrary function of by plus ax. And now we can substitute values of a, b, c here. C is 0, so we have 0x. We will consider phi 1 as first function for this d minus d dash. B is 1, that is 1 into y, plus a is also 1. E raised to 0x is 1, therefore we have arbitrary function of y plus x. That is going to be the part of general solution corresponding to the first factor d minus d dash, arbitrary function of y plus x. So it is very easy. What we have to do is we have to find out values of a, b, c. For that we will compare given factor with this standard form, and we will obtain that b is 1, a is 1 and c is 0, and using this formula we are able to write down this arbitrary function of y plus x. Similarly, now we consider another factor and we find out what is ABC for that factor. Another factor is d plus d dash plus 1, so that we write here d plus d dash plus 1. Coefficient of d is b, that is 1, and if we compare this term d dash with minus a d dash, then we find that minus a equal to 1, that is a equal to minus 1. Similarly, if we compare the constants, here constant term is minus c, here it is 1, that means minus c equal to 1, that is c equal to minus 1. So now we substitute values of a, b, c in this formula. Here b is 1, which is non-zero, therefore we will use this formula. C is minus 1, and here we have c divided by b, that is minus 1 divided by 1, which is minus 1, and we have e to the power minus x. And here we will consider another function phi 2. B is 1, therefore we have y. A is minus 1, that is minus x. Therefore we have e raised to minus x times arbitrary function of y2 minus x. E raised to minus x times arbitrary function, which is denoted by phi 2 of y minus x. This is the general solution, where phi 1 and phi 2 are arbitrary functions, or we can simply write that phi 1 and phi 2 are arbitrary. Here we have simply used this formula. We compare linear factor with this, we find out ABC, and we substitute values of ABC in this formula, and we take care that while using this formula b is non-zero. If b equal to 0, then we will consider c divided by a times x, arbitrary function of by plus ax. But here for both the factors, coefficient of d is non-zero, therefore we have used this formula. Now we consider another example. Here our differential equation is given in this form. We are familiar with all these notations. R is the notation for partial derivative of z with respect to x, which is of second order. S is second order partial derivative of z with respect to x and y, and P is the notation for del z by del x, and we recall all the notations. Q is the notation for partial derivative with respect to y, and T is the second order partial derivative with respect to y. Sometimes they ask the problem in this type of notations also, so you must be familiar with all these notations. Here we have r, that is del square z by del x square, minus s, that is del square z by del x del y, plus del z by del x equal to 0. And this we can write in symbolic form as d square minus d dash plus dz equal to 0, that I have written here. And this is our operator capital F, and it is also non-homogeneous degree of this term is 1 and degree of these two terms are 2. That means degree of each term is not same. That is, this function of d and d dash is non-homogeneous. But we can take d common from each term and we have d minus d dash plus 1. So here fdd dash is reducible operator. We are able to write it as a product of two linear factors of this form, bd minus ad dash minus c. Now we have to compare these two factors with this standard form which we have taken. So first I consider this linear operator or linear factor. So if I compare d with this factor, I have b equal to 1 and a and c both are 0. And what was the formula? We have e raised to cx divided by b, arbitrary function of by plus ax. C is 0, that is we have e raised to 0x divided by 1, which is e raised to 0x. Arbitrary function of b is 1, that is y, a is 0. That means we have arbitrary function of y only, that we will denote by phi 1. That is corresponding to this linear factor. Similarly, we can decide ABC for this factor. If we compare this d minus d dash plus 1 with this, we can see b is 1, a d dash equal to minus d dash, that is a is also 1, and 1 equal to minus c, that is c equal to minus 1. So what will be the part of general solution corresponding to this? So that is going to be e to the power c by b. C is minus 1, b is 1, that is c divided by b is minus 1 into x. Another arbitrary function denoted by phi 2, b is 1 and a is also 1. That is we have e raised to minus x times arbitrary function of y plus x, and corresponding to d it was arbitrary function of y. And we write down general solution by taking addition of these two, arbitrary function of y plus this one corresponding to this factor, e raised to minus x times arbitrary function of y plus x, where phi 1 and phi 2 are arbitrary functions. This is the general solution of this equation in which fdd dash is non-homogeneous. All these are homogeneous linear partial differential equations with constant coefficients, and in which we have taken this operator capital F, which is non-homogeneous. This is another example. S is del square z by del x del y, P is del z by del x, Q is del z by del y equal to z. And in symbolic form, this is d dash, this is d minus d dash z equal to z. And if I shift this on this side, and I can take z common, and this is my capital F, d dash plus d minus d dash minus 1, z equal to 0. And it is non-homogeneous. Obviously, degree of each term is not same, therefore fdd dash is non-homogeneous. And now we can see that here we can take d common, so we will have d dash plus 1 in the bracket, and here we will take minus 1 common, so we are left with d dash plus 1. So that I have written here. Or I can combine these two, d dash minus d dash, and these two, d minus 1. And here now I take d dash common, and I am left with d minus 1, and here I can write 1 times d minus 1. And now we again take d minus 1 common, so we have d dash plus 1. So now we have to again compare this d minus 1 with bd minus ad dash minus c. So if we compare, we find that b is 1. There is no d dash here, that is a equal to 0, and here minus 1 equal to minus c, that is c equal to 1, and b is non-zero. Therefore the solution corresponding to d minus 1 will be e raised to cx by b, arbitrary function of by plus ax, and what is c and b both are 1, c by b is 1, that is e raised to x, arbitrary function of b into y, b is 1, that is y, plus ax, and a is 0. Therefore we have e raised to x times phi 1 y corresponding to d minus 1. Now for d dash plus 1, we have seen in previous lecture that if our linear factor is in this form, a d dash plus c, then the part of general solution corresponding to this is e raised to cy divided by a times arbitrary function of ax. So here we compare this with a d dash plus c. So we find that a is 1 and c is also 1. So we have e raised to minus y, arbitrary function of x, that we will denote by phi 2. So corresponding to d minus 1, what we have written, corresponding to d minus 1, it is e raised to x times arbitrary function of y. So now we are combining both the results, e raised to x times arbitrary function of y plus e raised to minus y times arbitrary function of x, and here these two are arbitrary functions, phi 1 and phi 2 are arbitrary. So here new thing is we have this type of factor a d dash plus c. Okay, and this you have to do as a rough work. You should not write all these things in this way. You can do rough work and then finally you can write down the general solution. So first you show that your function f d d dash is product of linear factors. So you have to show this part, that f d d dash is reducible, or we are able to write f d d dash as a product of linear factors, and therefore corresponding to each linear factor you write down the solution by comparing with standard form. So in this way we can easily answer this type of questions. Again we repeat that we are discussing homogeneous linear partial differential equations with constant coefficients in which f d d dash is non-homogeneous. We have discussed the case of homogeneous f d d dash in lecture number 1 to 4. In lecture number 1 to 4 we have shown that if f d d dash is also homogeneous, then how to solve this homogeneous partial differential equation. And from lecture number 5 we are considering those problems in which f d d dash is homogeneous and how to write down the general solution in this case. Now in upcoming lecture also we are going to discuss the non-homogeneous f d d dash and how to solve the partial differential equation which is homogeneous with constant coefficients. And today this is enough. In this lecture we have discussed the non-homogeneous f d d dash, and we have discussed that if we are able to write f d d dash as a product of linear factors of this form, then the part of general solution corresponding to this type of factor is e raised to cx by b, arbitrary function of by plus ax, in the case that b is non-zero. If b equal to 0, this will not work. In that case, if a is non-zero, then we will write e raised to minus cy over a, arbitrary function of by plus Ax. And as a particular case, suppose our linear factor is in this form, a times d dash plus c, then we will consider e raised to minus cy over a arbitrary function of ax. This is the part of general solution corresponding to this type of linear factor. And in this lecture we have discussed examples based on this thing. Now in next lecture we will see that how to write down the general solution if this type of factor is repeated. If we have repeated linear factors of this form or of this form, then how to write down the part of general solution corresponding to repeated linear factors of FDD dash, that we are going to discuss in upcoming lectures. So I stop here. Thanks for watching.